Hello, welcome back. I'm Scientific Sue and it is UCD Festival, and this is part 2 of my really rubbish science show. So yesterday I was looking at the types of litter, and with your help we investigated which types will dissolve in water and which types won't dissolve in water. And 2 of the materials that I looked at were packing peanuts. These packing peanuts here, filled with lots of air, they're made from cornstarch, and when we put water into them and we shook them for 10 seconds, we found out that these do dissolve. So basically, if we've got litter that dissolves, it looks ugly, but in terms of the environment, it helps. It disappears very quickly and can be broken down, not just by shaking, but by biology, by bugs and bacteria. So that's when we call it biodegradable. So something's going to maybe eat it and poop it out, etc. We also looked at polystyrene. So this is puffed up polystyrene with lots of air in it, so it's called styrofoam. And we found out that the styrofoam, didn't matter how much we shook it, it kind of floats. So that allows me now to talk about floating and sinking. So we looked at that yesterday as well. And the key thing about floating and sinking is to do with density. Now, as we kind of go through this show, this particular one, I'm really looking just at plastics. And plastics come in all different shapes and sizes, and they have different densities. So if it's a big, thick bucket, it's going to sink down into the bottom of the sea. If it's got a density though similar to seawater, it's going to be submerged. It's going to be underneath the water, and it's just going to be floating in between the top and the bottom. If it's lighter than the density of the seawater, it's going to float on top. But it's this litter here that's in the middle of the oceans that we worry about, because that's where our whales and our turtles are swimming and other fishes, and they're eating that litter. Now, talking about eating litter, what we're going to do here is we're going to look at the polystyrene and look at how we use it now for chewing gum, right? But first of all, let's kind of find out what's happening here. So I've got the polystyrene pieces here, and I've got another liquid. So this liquid is called acetone, and many of you may see it in the form of nail varnish remover. And it's a material that you do not want to have anywhere near a lacquered surface, because it will dissolve some materials. Not all plastics, but some plastics. So let's kind of pour some of it first of all into here, okay? So we're going to go in. I can hear it fizzing, and wow, my goodness, it has gone down to practically nothing. Right, so let's kind of bring this a bit closer now. So I've got a big jar full of this here now, okay? And when I put the acetone in, fizzing away again, and it just dissolves down, and we've kind of got that kind of plasticky liquid in the middle there. The liquid it's dissolving in is called a solvent. So water is a solvent for the packing peanuts made from cornstarch, but is not a solvent for plastics. For us to dissolve plastics, not some plastics, we've got other chemicals, and one of them is being acetone. Now, what I'm going to do here is I'm going to lift this material out and let you see it. Okay, now, it's a bit messy. See that? It's really stringy. And so we've made a liquid plastic. And so much of our plastics can be recycled, and they kind of go into this kind of liquid phase, and then we can kind of put it into a mold and we can shape it. So I'm just getting rid of the acetone there, okay? And I want to then just end up with this liquid here. And I've got a little mold. It's a nice little shape here, a little flower shape. And I'm going to get my plastic here, and I'm going to pour it into that mold. And as it's moving from my fingers, I want you to kind of look at it, because it's very stringy. Can you see that? Okay, and it's kind of starting to dry as I'm moving it through the air. We've got those kind of strings. And this is evidence that it's made from not just one molecule, but a string of molecules. And we call those strings of molecules polymers. Now, oh, look, it's very messy. Now, what is this reminding you of? I've got all of this kind of mess on my fingers. Right, so I put that into that mold. And so lots of the plastics can be recycled. And this is what they're used for. So what I've got here, it's genius. So it's gone into a mold and it's dried. It's also recyclable again, but rather than use those plastic ring pools which can trap animals in, remember I showed them yesterday, these ones here we keep and we put our cans on there, we go into the shops and then we take them away. So I love this. Not seen it in the shops at the moment, but hopefully this is going to come into the shops very soon. So we're using the plastic to make something which will get rid of another source of plastic and is environmentally friendly. It can be reused again and again and again. So we just saw there that the polystyrene was very kind of runny and stretchy, and that's because it's made up of long chain molecules. And what we have is one molecule that's repeated again and again and again and again. And we call these monomers. And then when we make them into long chains, they become polymers. And some materials that we have, we use the word poly in front of it. So polystyrene, polythene, and polyester. So what I want you to do is I want you to kind of think about making maybe a Lego car. So this Lego car will have about 20 to 30 little blocks to it. And if I made another one identical and another one identical and another one identical and then join them all together, that's when we kind of make a polymer. And they're not they're not small chains. They are very, 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 very long chains. Very, very noisy there. So that's our polymer. Now, lots of people love chewing gum, and chewing gum is now a man-made material. It didn't used to be. It used to be made from the sap from a sapodilla tree. So underneath here, I actually have a bubblegum factory and some of the natural sap that we get from the trees. So they kind of collect it from the tree. They cut the tree in crosses and then this white sap comes out. So there's my bubblegum. We're going to stick that there. And then they kind of process it and then they kind of put it into blocks like this, which are sent off to around the countries. Now, we can still get organic chewing gum, but it's very expensive. So what we're doing now is we are making our own. Now, if we are looking at this latex that comes from the tree, it looks like this. It's a white liquid, okay, and it flows and it's sticky, okay, and then what they do is they stir and stir and stir and heat, and then they kind of mix things in to make it a lot thicker. And that means then the chewing gum that we spit out, which we shouldn't do, but is spit out onto the ground, because it's made from plastic, means it will take years and years, decades even, for it to break down. But it never disappears. So I'm going to show you why. So first of all, let's make some. So I don't want a boring old white chewing gum. I want to have some yellow chewing gum. So we're going to put that in there. And what they do is they kind of add different chemicals in. So I'm going to put in some water there. And what I'm using for my polymer is something called PVA glue, polyvinyl alcohol. So I'm stirring this, and at the moment what I've got here is a mixture. So I've got my PVA glue that's made from those long chains, and I'm mixing it up now with water and some colouring. Of course, if it's in a chewing gum factory, we'll put flavours in there and we'll put sugars in there. And then we want to thicken it up. So to thicken this up, we're going to use a slime activator, because what I'm actually basically is making slime, because that's what chewing gum is. And so I'm going to very carefully measure out 30 millilitres of this material, this slime activator. I'm going to pour it all in, and then I'm going to stir and stir and stir. Wow, that was a lot of hard work doing all that stirring, but it paid off. Look what we have now made. So slime is a really weird material. If I treat it rough, it kind of acts a bit like a solid, but if I treat it gently, it flows like a liquid. Now, chewing gum is exactly the same. So if you kind of chew it, you can kind of pull it and it breaks, but if you treat it very gently, it's going to flow. Now, what I want you to do is I want you to imagine that this is the floor, okay? And whenever we look at the ground, the concrete, the road, there's lots of cracks in there, lots of holes in there. So I've got kind of, hello, got lots of holes in there. And what I'm going to do is I'm going to spit my slime onto the road. And it kind of sits there, and I think it's there, and that's fine, and the cars are going to go over it. Maybe someone's shoe's going to go into it, and if the shoe goes into it, it kind of sticks to the shoe, okay? Oh, you've got all of that there. But what we don't see is the fact that because when we treat it gently, it flows, it's going to start to go down through all of those holes. And so if the chewing gum isn't picked up immediately, then over time, over a couple of hours, we're going to find that a lot of it is going to end up going down into the ground. So here's a little bit of the slime that I'd made earlier. And here you can see this is all underground. So what I could do is I could kind of pick off the top. I can remove it. I can use a lot of expensive equipment to do that, but I cannot remove what's there. So when we look at the chewing gum marks on the roads and the streets, even though the council have spent so much money in clearing the top layer, we can't get rid of the marks because quite a lot of it has flowed, it's gone all the way to flowed down in through all the nooks and crannies. Chewing gum comes with paper. Chew it, wrap it, bin it. It costs $1.50 for every item of chewing gum. We pay what? 30 cents, 30 pence to get it, and then it's 5 times that amount to kind of lift it off. Oh look, it's good slime though, isn't it? Good slime, but not if it's chewing gum. Let's go over that again. So whenever we're looking at polymers, we can have natural polymers that we get from trees and plants, and we can have man-made polymers, which we get in the laboratory. So our slime is a man-made polymer. And the word polymer means that we've got one unit, one molecule that's joined to another, joined to another, and joined to another, and it gives us these wonderful long chains. And for me to be able to make my slime, I had to put in a slime activator. And the simplest way that I could come up to describe that was coming up with this little demo here. So what I've got here is some ping pong balls and some Velcro. And we've got these monomers all joined together, these little mers. And whenever they're in the bowl together, they don't stick together. They can kind of move. But because of frictional forces, because they're kind of going like this, like snakes in a bowl, they're much thicker much thicker than water. But our slime activator is made up of small molecules, like a bit bigger than water, but they're able to flow really easily. But when I add them into the polymer, what they do is they join all of those chains together. It links those chains. So you sometimes hear cross-chain linking when we're dealing with this type of chemistry. Polymers and plastics, the same thing. Now, what I want to do is talk about another polymer, a polymer that we find inside nappies. And so what I've got here then is I've got two types. So the crystals are called sodium polyacrylate. These are very, very tiny crystals. These are what we get inside the nappies. So I'm going to put that into that jar there. So we're going to place that there. And these are much bigger granules, and this is what gardeners use. And they use it for exactly the same reason that we have it inside our nappies. Okay, so there we go. So that's gone in there. And let me see, they just kind of cover the bottom of the jar. And into both of them, I'm going to pour 250 milliliters of water. So they're going to go in there. Okay. Fantastic. Now, with that going in, while the science is working, okay. Oh, much smaller crystals. Ready for this? Ta-da! Oops. It sucks up all of the liquid. It is amazing. I've got another amazing toy here. Let me show this to you. Okay, this is my Hoberman sphere. So yesterday I used this to kind of talk about how hot air expands and rises and then cools and sinks. And it's that expansion and contraction of air that gives us the wind that makes the litter blow around the countryside. And we also use this to talk about hot water, because water expands and rises, and then when it cools, it sinks. And that's what gives us the ocean currents. And it's those ocean currents that moves the litter in the oceans all around our continents and the other oceans and seas. Today, I'm going to use this for another thing, because what this is going to do, this is the crystal, and when I put the liquid into it, it gets really big, and it locks all of the liquid inside, but eventually it will release the liquid, and then we go back to, I'm trapped, go back to our original size. So we can trap it in, and then it expands. So we kind of lose the liquid and it goes back to its original size. And this is why the nappies are so bad for the environment. Because even though the tissue will break down, these crystals, like glass, will never break down. As soon as they're in the soil, they are there forever. Now, in terms of litter, you won't believe what I found as I kind of walk around. And in the summertime, I have found used nappies left on benches in parks next to a bin. And what we've kind of got to think about now is the fact that animals love eating litter. So what I've got here, okay, I want you to imagine that this is the mouth of the little bird, and then this is its intestines. And it's kind of going to go down into the stomach area. From the stomach, it's going to go through the intestines, and then it's going to get pooped out. And birds, well, they love eating seeds. So I can kind of feed my little bird some seeds, and they're going to go down its throat. They'll get broken up, and then they will come out as little bits of poop. Oh, I have to go in first. There we go, little bits of poop. Now, sometimes though, as well as the seeds, we'll find bits of litter. This is a very tiny part of a balloon. Balloons, when they're released, they go up into the sky. It gets really cold. The latex that they're made from, the rubber, turns not into stretchy but very brittle, and it shatters, and very tiny pieces then come down to the earth, and big pieces, and the animals eat them. And so what we can do then is we can kind of start feeding, and I put, phew, we got some through. So it fed, but the food came through. And, now I've got the plastic. If it's a small piece of plastic, it will pass through the tube. But if it gets bigger and bigger, it blocks the tube. Now, these crystals again, so we're going to put these crystals now. So imagine that a badger has come across this nappy and the badger's decided, ooh, that smells quite nice, and it's going to eat the contents of the nappy. I know it's quite gross, but there's going to be some of the crystals may not have absorbed any liquid. So those crystals are going to go into the intestines of the badger or the stoat or the fox or the rabbit or the rat. And whenever they then have a drink, it's going to end up being inside their system. And then when they have another drink, that drink can't go anywhere. And when they decide to eat, that food can't go anywhere. So they end up eating and eating and eating, and we're finding that everything gets blocked up. And then, unfortunately, the animal dies. So we've got to be very careful about our litter. We have to think about where will it go and what will it do. So I've come to the very last demo of this session, and so before we do it, I want to kind of revise a few things that I was talking about. So mainly in this session we've been looking at plastics. Plastics are made from polymers and they do not dissolve in nature. In fact, it could take between 20, if it's a thin plastic bag, to 200 to 2,000 years for them to break down, but they don't disappear. They just go into smaller and smaller and smaller particles, which means the smaller animals are eating them. And who eats the smaller animals? We do. So we don't want the plastics there. Now, scientists are amazing. So they have been inventing new materials. So what we've got here, it looks like plastic, feels like plastic, but it's made from cornstarch. And as we saw earlier, cornstarch does dissolve in water. The problem, what I'm going to talk about now though, is the fact that as we saw, when it's windy, so the hot air's rising and the cooler air's coming in, it moves the litter on the surface of the planet. And some of it might go down drains. And as we saw, if it's denser, then the liquid is going to sink to the bottom. It could be suspended if it's got the same density, but if it's lighter, it's going to float, and that both the suspended litter and the floating litter will go down the drains. But eventually, the litter on the bottom is going to fill up. The bits that are moving are going to reach grills and will block, and we're ending up with our drain system becoming blocked. So I'm going to just move this a little bit closer this way. Okay. Oh, that's a bit noisy, isn't it? There we go. And so what I've got here is I've got two river systems which are blocked. So near me, I've got four rivers: the River Con, Lagan, Loop, and Knock. And I live very close to the River Loop, and something disastrous happens pretty much every time it rains. So imagine the litter's going down, it's blocking up the drains. And that means that when it's stormy, because they're called storm drains, when all the rain is coming down from the fields and it's going down the storm drains to go to the rivers, to go to the sea, taking litter with it sometimes. If the rivers are blocked, if the drains are blocked, then they can't go down that river, and it can't go down that river. So the water that should have been split between four rivers is now only going to go down two. Now, what I've got here is a little device which is holding Mentos for me. 4 Mentos. And so I'm going to put my bottle in there. And so I've got my Diet Cola. That's what they say we should use. And I'm hoping that when I pull a little lever here, that's going to allow the Mentos to go down into my cola. And instead of it just leaving slowly, hopefully it's going to leave really fast, and it's going to have a choice of 4 routes to go down. Unfortunately, these two are blocked, So it's only going to be able to go into these 2 rivers. But look, I'm using very big measuring cylinders to make sure I don't get a mess. Okay, now when we finish this, I just want you to keep thinking. When we put litter on the ground, where does it go? What does it do? So 3, 2, 1. Oh my goodness! We got a flood! Oh my word! You could do this at home. I built this so you can become your own engineers. Now, tomorrow, we're going to be looking at smart materials. We're going to be looking at graffiti and again at some of the things that litter does to our environment. So I'm Scientific Sue. Thank you so much for watching and I'll see you again tomorrow. Bye!